It's not even on. Can we go over who sends what in WebRTC very specifically? Yeah, sure. I can do that. So you're going to open up two tabs, start your video on both, and then in one of those tabs you click Start Connection, whatever I put on that button, but to establish the WebRTC connection. When you click that button, the browser that you click that button on is going to send the offer. So the offer message is sent by that client. So you're going to forward that offer to the other client. That client is going to receive the offer and send back. I always want to say accept, but that's in the WebSocket handshake. Sends back someone help me out. The answer. Going to send back the answer. So the other client sends back the answer, you get the answer, you send it back to the person who sent the offer, the client who sent the offer. And then each of these clients, both of them, are going to send their, man, why do I always blank on the vocab? Can I blame it on being 10 in the morning? They're both going to send their candidates. They're both going to send their candidate messages, which could happen simultaneously. It could happen immediately after that accept goes through. These can happen at any time. It's up to the clients when they want to send them. When it's ready, they got to go contact the STAB server, get the response, and then once they do, they're going to send it to you. So both of them send the candidates, which could be happening simultaneously. So your code has to be handling this properly, handling multiple connections simultaneously, because these messages might actually be sent simultaneously. They're both going to send them, and then you send each other's candidates to each other. And they might send multiple candidates as well. You need to be able to handle as many candidate messages as they feel like sending. In my testing, I usually saw two. There's going to be one with actual information and one to say, I'm done sending my candidates. But any candidate message that you get, just send it to the other one. So you might have 6 messages. The offer goes to this one. They'll send back an answer, and then candidates coming from both of them that need to be sent to the other, and probably multiple candidates. So those are the messages that'll be sent. And those messages might be sent seemingly back to back, too. So you do have to be careful about the payload length. You should be careful about reading only those bytes, and then the other bytes from the TCP socket might be part of the next message, because they might be being sent back to back. Can we get a live leak code hard grind? Maybe during review week. That would be fun. I would enjoy that, honestly. But maybe during review week. You don't have anything specific on the schedule? I don't know if it's really related to 312, so not outside of review week. Do we need some kind of circular buffer for homework 3? Is it possible to get more than WebSocket packet at the same time? So I know I just said that this is possible, but I didn't see it in my testing. If that was your only bug, I would have, at the very least, I would have a lot of sympathy for that. I'd probably give you any points you got back. So I'll say no. It's something you should be aware of in general, but it's not something I've run into in the homeworks. Now, if everything's absolutely broken and just your specific implementation is running into that often, then maybe it is something you have to do. So I don't want to just blanket say you don't have to worry about that. But if you don't implement it and it does work, I ain't going to be mad at that. As long as your stuff works, I'll be happy. For the message, are they sent in the frame form? Oh, yeah. For WebRTC, everything's sent over WebSockets. So when these two clients connect, they're connecting as WebSockets. You're putting them both in their own infinite loops on separate threads, and they'll have shared memory so they know about each other's connection like I demoed in class. And then over those WebSockets, you're going to get the WebRTC messages. So all those messages that are sent, it's all WebSocket frames, and you're going to send the WebSocket frames to the other client. So the problem is the clients need to communicate these WebRTC messages to each other. So we need some mechanism where when I get this offer, when your server gets this offer, we need to be able to let the other client know that, hey, you got an offer for a WebRTC connection. We can't do that with just plain HTTP because this client would have to send a request, and then we could say, like the client would have to say, hey, do I have any offers? And then we respond with the offer. With WebSockets, we can do the server pushes. We can just say, hey, you got an offer, and let them know over their WebSocket frame. So that's why it's one reason why we don't talk about WebRTC until we have WebSockets. The alternative would be like polling or long polling. But I didn't make you implement those in this class, so we wait till WebSockets. Can you send? I feel like my brain just like, those words don't go together, but I think it's a me problem. Can you send the chat WebSocket frame back as a byte string? Yeah, that's a me problem. As a byte string, I'm not positive what you mean by that. I want to say yes. Everything in the WebSocket frame and everything in HTTP, everything that goes over the internet is bytes. Everything that goes over your TCP connection, it's all bytes. Everything is bytes. So when you're sending text as your chat message, when you're sending that over the WebSocket connection, you're only sending the bytes of the string. So you're not sending like a string itself. You're encoding that in the bytes using UTF-8 and then appending those bytes to the end of the WebSocket frame. Same, just like in HTTP, you had to encode the strings to put it as the body of the HTML response, and then get the content length, which is the number of bytes of that payload after the string is encoded in bytes. You're doing the same thing here with WebSockets. You just have the payload and payload length instead of body and content length. Same idea, though. It's all just bytes, and the payload is the number of bytes. So, for example, if you have non-ASCII text in your string, you need to convert that to bytes to get the payload length, or else you're going to have the wrong payload length, and things are going to break. All that stuff still applies, all that stuff we talked about. I don't think I brought that up again when we were talking about WebSockets. I kind of took it for granted at that point. But everything's bytes. We're always, always, always in the world of bytes when we're talking about TCP and these lower protocols, lower level protocols. The internet in general doesn't really know what a string is. It's just content that has a content type of text. And it's up to the browser to actually interpret that as text. The internet itself, when packets are going through the internet, doesn't understand what a string is. TCP doesn't know what a string is. So everything we send is bytes. Nice, a good, old but a good one. I think people will be happier with a Homework 3 extension. I mean, students are always happier with an extension until the next deadline comes. If I give an extension on Homework 3, that's less time for Homework 4 in the project. I had a disaster. I think that's what Rin's talking about here, right? There's, I got roasted one semester for giving an extension because it interfered with the project. Like, the class hated me. They loved me when I gave the extension, but they hated me when they realized that two things were due in the same week later on. Like, yeah, because I gave an extension. There's something due every week. If I extend one, it interferes with the next thing. You look at Write My Professor to find out all about that. They hated me for that. So I don't really like giving extensions for that reason. The only extension I gave was over spring break because it didn't interfere with anything else. But what if I gave a 1 week extension? Now you're not going to even start thinking about Homework 4 content until I'm talking about the last week of content with Homework 4, which just doesn't work. Plus, you got 4 weeks since the thing was released. I don't know. I guess 5 weeks because it was released before spring break, but I usually don't count spring break as anything. All right. If there's anything else in there I missed, please at me and repost it. Looks like just a bunch of talk about binary. This came up after Monday's lecture too. I don't know. I want to know where that confusion's coming from because I'd like to clarify it. The difference between bytes, bits, hex, binary, they're all the same thing. Everything's ones and zeros. in our code, we usually get them in chunks of 8, and we call them bytes. So when you read from your TCP string, you're getting an array of bytes. And then you're reading these bytes 8 bits at a time. So there's no difference between a byte, hex, binary. They're all the same thing. You're getting an array of bytes, which are the actual bits. And then for WebSockets, we actually do care about the individual bits, but there's no like bit data type. You can't have a bit as a data type. Unless you create it, I guess. I don't know. I don't know if that makes sense. But you can't have like a bit. You have a byte, and then you can read the individual bits to figure out what they are. But you never have your data in bits. And you don't necessarily have like your data in binary, but at the same time, your data is always in binary, because that's the only thing that actually exists in the computer is binary. Everything else, anything that we do to derive meaning out of that binary is just an illusion. There's no string, really. There's never a string. It's just a whole bunch of binary. So we're always in binary. So when you're reading the bits, you're leaving everything in bytes. There's still bytes, the data type, but you're reading the individual bits. You're actually caring what the bits are. Same when you get your payload length as an integer. An integer is just a bunch of bytes, and we pretend that it represents a number, but it's really just a bunch of ones and zeros still. So you can access those ones and zeros. That's what we're doing in homework 3. We're actually accessing the ones and zeros and caring what those ones and zeros are, but they've always existed. Every time you've ever had an int, it's just a bunch of ones and zeros. It's all binary. Always binary. Yeah, it's 10:15. I haven't started lecture. All right, let's talk about authentication. I know I can do, so we have time for that. I know I can do these slides in less than 50 minutes, so I'm fine with that. Why is that funny? Because what I want to do in a lecture is answer your questions. Whatever questions the class actually has, that's what I should be focusing on. So if I had 50 minutes of slides and I'm like, I'm not answering your questions, I'm just covering these slides, I don't think that's to your benefit. Especially since you're all asking about homework 3 and I'm talking about homework 4, which you're going to ignore and not do homework 4 until 3 more weeks. You know, I'm kind of realistic that a lot of you won't fully pay attention today. Like, you might get the high-level concept of what authentication is, but you're not going to think about it, how it applies to your code until several weeks. So I know a lot of my words during this lecture will be just for the video. All right, so let's talk about user accounts. You've seen these many times. We know what user accounts are. We intuitively know what authentication is. It's when you have a registration form. We have this in 2 parts: a registration form and an authentication form. You register for an account. You set a username and password at minimum. Some sites you need an email address as well, or your email address becomes your username, etc. And then you authenticate by providing that same username and password to that site. And then the site says, okay, you're good, you're authenticated, and then you're logged into that site. This is the functionality we want to talk about today. And with very few exceptions, maybe the cross-site request forgery might be an exception, that token, depending on how you look at it. But with very few exceptions, we're treating everything in isolation. Whenever we get a request, we're delivering the same content to everybody, even if that content is generated from an HTML template. It would be the same for everybody. Everybody gets the same images. Everybody gets the same chat history. Everybody gets the same exact experience. Now we want users to be able to authenticate so they can get a personalized experience. This is something we expect from our web apps. I want to log into a site and get my experience. I want to see my DMs. I want to see my following list. I want to see that kind of stuff. Content catered to me, at least to my account. Oh my goodness. There we go. So, and we've seen these, obviously. I don't have to dwell on what authentication is. We've all used this from the client side. But one thing you've noticed from a lot of these is you'll have to verify your email address. You'll sign up for an account, and they'll say, okay, cool, we sent you an email, respond to that email, and then we can talk. But until you respond to that email, we're not doing business with each other. It's not happening. You have to go and verify your email. So a lot of sites have been doing this lately. I just want to talk about why they're making you verify their email. The short answer is bots. Bots are out there, and they'll create thousands, millions of accounts, however many accounts they can, and try to just bombard a site with whatever they want, whatever the bots are doing, whatever their specific purpose is. It's different for any different bot. But if you ask them to verify their email, it's not that the bots can't, the writers of the bots can't verify an email. It's that they need a legitimate email address to be able to verify. They can't just come up with a random email address. It's a lot harder for a bot to fake this, to be able to answer that email, respond to it, and generate their account. So this really cuts down the bots. And I've actually seen this. I had a Q&A site. I might have mentioned it in this semester before, but I had a Q&A site for 115 back in the day. It was, I don't know, probably like 3-4 years ago, not too long ago. But I had a Q&A site. It was like a Stack Overflow clone that I used in place of Piazza because, I don't know, I was sick of Piazza that semester. And it actually liked the way it worked. I might go back to something like that. Something about Piazza invites duplicate questions. Nobody looks at this question history. And the one nice feature of this Q&A site was when you started typing a question, it would give you suggestions like, hey, your question looks a lot like these 3 questions that were already asked. And then the student could click those and be like, oh, it was already answered. This is great. Yeah. Piazza does that when you're typing a question? Oh.
Nobody looks at it, though.
It's okay. So something about that feature it's got to be broken because if nobody's using it, there's some. I mean, I never knew it existed, but I guess I don't ask questions on my own Piazza either, so I might not have noticed. It probably doesn't show up when you do posts then, right? You were just posting, I forget what they're called, but comments and not questions?
No, it shows up when you make your question.
Only questions, though? And I've never done a question on my own Piazza, so I don't remember. But that is interesting. I'm going to have to try that. I'm going to try that and see how that works. So anyway, I had this Q&A site, and I released it. I said, here, use this site, go ask questions. And then I looked, and I saw like hundreds of registrations. And there were hundreds of students in the class. So I'm like, holy crap, they're actually signing up for it. This is great. This is fantastic. And then like a few days later, I checked how many registered again, and it was in the thousands. I'm like, whoa, people not even in the class are signing up for this. This is great. And then eventually I hit the tens of thousands and eventually hundreds of thousands. And I'm like, okay, something's going on here. So I looked at what the email addresses were, and they were just clearly randomly generated strings. Obviously bots just creating thousands and thousands of accounts. And I could see the server logs just constantly hitting this site with what were obviously bot traffic. They were creating several per minute. Sometimes they were creating several accounts per second. Just completely spamming the server. But I had email verification set. They couldn't verify any email addresses, plus it was set so you had to verify a buffalo.edu address. So they had no chance of getting through at all. So they had to verify their email address. They couldn't verify the email address, so they couldn't post anything. So they couldn't actually do any damage to my server. They couldn't ask questions or really interact with it. So with that verify email, which luckily I had checked and didn't just say, it's open, students just use this, whatever. Luckily I didn't have that because that would have been bad. It would have had bot traffic all over my site. What I added, there was an option. I used an open source library. This is open source software that I used to do this. I didn't code it myself, but it had an option that to add CAPTCHAs to it. So I added CAPTCHAs, and that completely got rid of the bots. They couldn't even create accounts after I added that. So they couldn't verify their email after they created accounts, so they couldn't post. But with the CAPTCHA, the bots just got completely stuck. They couldn't do anything. So with those two things, it is actually real. Like I thought, who the hell would actually want to attack my Q&A site for 115? But the bots are out there. They're just scanning everything. They're looking for whatever they can find. And they found that. It must have been a well enough known open source project that somebody wrote bots specifically for that, is what I'm assuming. I don't know. But for whatever reason, however they did it, they found a way to bot it. And luckily I had some preventions in place. So it's annoying for regular users. It's one of them things that's annoying for any legitimate user. We have to do one more step during the process. We have to fill out this CAPTCHA. We have to verify our email. But that is an actual threat. The bots are out there. I've seen it. I used to show the database, but I have to remember how to log into it if you want to see it. But it's just hundreds of thousands of bots that just bombarded the thing. Anyway, so when we authenticate, there's an implication here. You have your registration form. You have your login form. The implication is that the server has to store your password. And that's really what we want to talk about today. So authentication itself, like, you can figure that out. You have two forms. You're going to get requests with this information. On registration, you're storing username and password. On login, look up the password for this username and check if the passwords match. Like, you can build authentication. There's not much I really have to say about that. But what I do have to talk about is, how do we store these passwords? So if we're storing these passwords on the server, ideally, attackers won't be able to access those passwords. But what if somebody gets a successful SQL injection attack and is able to recover those passwords and gets everybody's username and password? I hope we all agree that that's bad. That's bad. And the solution is never store your passwords as plain text. You may or may not have heard of this many, many times in your life so far. But never store passwords as plain text. Even if there's not an attacker attacking that database, the sysadmins, anyone on the DevOps team, anybody with access to that database has all of your passwords. Like, for your, you have your Twitter account. I'll pick on Twitter here. You have your Twitter account, you log in, you create your account, and you log in. Do you really want every dev, at least anybody with access to the production deployment, do you really want everybody there to have access to your account? Do you want anybody with access to that database to have access to your account? Probably not. I would hope, I would assume that. You want them to have access to all of your private content and all of your data. To some extent, they still have access to, like, your DMs. They can read them, but they can't post on your behalf on your account. I mean, I guess if they have access to the database, I guess they could find other ways, but they won't have your password necessarily. I mean, now I'm thinking about how I would attack it. You would just replace the password in the database, and then it's game over. But you don't want them knowing your password regardless. So the level of security we want is that even the sysadmin wouldn't be able to know your password. That's the level of security we want. Because we don't want this big treasure trove of passwords stored in a database. That's a very lucrative target for any attacker or anybody looking to do nefarious things. That's a very lucrative target. We don't want that to exist. So this is why we hash passwords. We're not going to store passwords. We're going to store hashes of passwords only. Well, I shouldn't say only, but we're going to store hashes of passwords. Does the school know my UBIT and password? No. They absolutely should. I mean, I wouldn't be overly surprised if they messed it up, but they shouldn't know your password. I mean, UBIT messes up other things also. But I would hope that that's something that they're doing right, that they don't know your password. They should not know your password at all. So if you ever, I don't know if any of you ever tried this. I don't know. I haven't. But if you call up, tech support and you're like, hey, I lost my password. Can you just give me my password? They can't. They literally can't because they only have a hash of your password. So let's talk about what that means. So the goal is nobody knows your password. Nobody except you. Nobody knows your password. So let's see how we're doing that. So we're going to talk about hash functions. A hash function is a function that gives an output with a particular property, typically fixed length. And we like these properties for things like hash tables. If we have a fixed length, and we have a hash table where we have that many 2 to that length buckets, then we can use that hash function for our hash tables, and things are nice and everything. Hash functions do not necessarily add security. This is just a misconception. I hope to clarify. I say this all the time when I talk about hash functions. Hash functions are not made for security necessarily, but we do have something called cryptographic hash functions, which are made for security. So just because you have a hash function doesn't mean it's a hash function made for security. If you have a hash function that's made for a hash table, don't use that for security. For the love of God, don't use that for security. It's not made for that. It probably can be easily reversed. Don't use it. When I say, I'll make this distinction now, but later in this lecture, after this slide, I'm just going to say hash function. When I say hash function, I mean cryptographic hash function. So I'll add to the confusion even after this slide. But just know that there are many, many, many hash functions out there that are not made for security purposes. A cryptographic hash function, on the other hand, is made to be a one-way function, and its purpose in life is to take an input and generate an output such that you can't take that output and go back to the input. It's a one-way function is its purpose. There are no mathematical proofs that they are one-way functions, but we kind of just hope really hard that they're one-way functions, as most security things work. When we talk about encryption, encryption works the same way. We just hope really, really hard that it's secure. And that's good enough for us, you know. But this is supposedly a one-way function, hopefully a one-way function, the hash functions that we use. It's kind of scary when you think about how encryption works. It really does work on that. Encryption and security, we just hope that it all works. But somebody could break absolutely everything, potentially. Or maybe not. We don't have a proof that it's impossible, but we don't have any evidence that it is possible to break things. It's an interesting thing. Anyway, so it should be very easy. If I have a password and I want to hash it, it should be very easy to compute the hash. And this is the SHA-256 hash of the string password. It should be very easy to compute that hash, but should be impossible-ish, physically, practically impossible to be able to take this hash. If I didn't tell you what this was a hash for, you should not be able to take that hash and compute the plain text or a plain text that generated it. That's the feature we want. I say a plain text, I might be getting a little too into the weeds here, but there will be multiple inputs that'll generate the same hash value. Some we call the hash collision. And if you can generate any of those that output this hash, then those will all work as your password. So technically you have multiple passwords because they all map to the same hash, in theory. But the goal is that we can't take this and compute compute being the key word there, the plain text, a plain text that generated it. That's what we like from our hash functions. And you can play with these. Here's the SHA-256 is the algorithm I'll pick on during this lecture, that I'll use during this lecture. And you can use these. There's an online calculator. We can compute some hashes, which you can do to see hashes if you want. I'll give a demo if probably Friday. I'll give a demo of that. And this is what SHA-256 is. It's a lot of binary operations, a lot of bitwise operations. I don't fully understand how SHA-256 works. I don't know. It's just never interested me, all the low-level details of it. But we have these. But we have this circuit, effectively a circuit, and the output of this circuit is scrambled. You take the input, it goes through this, scrambles it, kind of randomizes things, not random literally, but shuffles things around. And then we go through the process again. The output is the new input. Run through it again, and just run through it multiple times until you have something that looks pretty scrambled up. And we hope that this is very hard to reverse. Hopefully it's really hard for people to have the output and just go backwards through this thing. Should be very hard to do. And nobody's publicly been able to do it yet. There's always a possibility that some hacker was able to reverse it and just didn't tell anybody and is cracking hashes at their leisure. Very possible. Unlikely, I'd say. But anyway. So we're going to hash these things. We're going to store only the hashes of these passwords, and we're going to not be secure. So we can compute the hash of our password, store just the hash, and we're still screwed. So you can't take that hash and undo it and compute a plain text that generated that hash. But what you can do is just use the hash function. Hashes are easy to compute. So instead of actually undoing and reversing the hash function and breaking SHA-256, what I'm going to do is just take SHA-256 and use it for its intended purpose. I'm just going to guess your password, hash it, and see if the hashes match. I'm going to do that until I guess your password. What's stopping me from doing that? This is what we call a brute force attack. I'm just going to keep guessing your password and hashing and seeing if the hashes match. Once the hashes match, I guessed your password. I'm done. I got your password. This gets scary. So this is a surprisingly common misconception. Just because you're storing a hash of something does not mean you're secure. So for example, say if I hash the answer to a question and my answer is either yes or no. It's a yes or no question and I store the hash of it. Or maybe, let me use this example. What if I store the hash of the answer to the lecture? Oh, that could have been a good lecture question for today. What if I store the hash of the answer to the lecture question? The answer can either be A, B, D, C, or E. Wow, my brain. Wow. Anyway, there's only 5 options. There's only 5 options for that. So what you're going to do is just try each of the 5 options, hash them, and see which one matches the hash that I stored. So if I give you the hash of the answer, you're going to be able to figure out what the answer is pretty easily. It's not going to take that much work. So just because you hashed doesn't mean you're secure. And I've seen this misconception. What I mean by surprisingly common, I've seen this even in peer-reviewed published work that said, we hashed it, we're fine, it's secure, don't worry about it. I'm like, but there were only like 50 possible values for that. It's not secure. And they're like, nah, we hashed it, don't worry about it. We hashed it, it's cool. Which always frustrated me because then in my reviews, I would get compared to that research and I had to explain to a reviewer, the frickin' researcher at the PhD level who is a doctor, and obviously I'm a grad student in this story, and I had to explain to them that just because you hashed doesn't mean you're secure. It's ridiculous stuff. So we need to talk about something called entropy. Entropy is the total number of guesses that you would have to make to be able to crack that hash. In this context, obviously entropy is a term that's used all over the place. But in this context, the total number of guesses you'd have to guess to guarantee that you guess that password. So for example, if I tell you that I have the hash of a single lowercase letter, the entropy is 26. If I give you the hash of the answer to the lecture question, the entropy is 5. And you can start increasing this entropy to make things harder to guess. If I say I have 2 lowercase letters, now the entropy is 667, the total number of possible combinations of 2 lowercase letters. If I introduce upper and lowercase, I start increasing this, and we can start seeing where our password requirements come from. If I have 8 characters, uppercase, lowercase, numbers, special characters, the entropy starts growing quite a bit. Not as much as we'd like, but the entropy does get up there. And we usually measure entropy as bits of entropy because these numbers get large and cumbersome and hard to read. We measure bits of entropy, which is the log base 2 of the actual entropy. We compute the log base 2 of the entropy. And as a general rule of thumb, we say if you have at least 80 bits of entropy, if it's going to take 2 to the 80 guesses to crack your password, then we give you the label secure. We just feel good after 80, generally less than 80, we don't feel good. Greater than 80, we feel good. Just a rule of thumb, but it's kind of what we go by in security. Yeah, quantum computers will destroy everything, though. I don't think quantum computers have something for hashing, but encryption, a lot of encryption will go away. We got defenses against that, though. Even quantum computers won't really break things. So, no internet. You know what? I have Wi-Fi. Well, you know what? That makes my decision easier. I didn't know if I wanted to go down that road or not. Give it an example. No, I'm not gonna. Thank you for the offer, though. But no, that makes my decision easier because I'm like, do I want to do the demo today? I might do the demo Friday of actually cracking hashes and showing entropy and stuff. But to the 80, if you do the math, if you do uppercase, lowercase, numbers, and special characters, it should be like 92, I think, the size of the alphabet, somewhere around there. And do 92 raised to the 8th power, your entropy is not going to be 80. So even if you're satisfying the common password requirements of 8 characters and a mix of uppercase, lowercase, blah, blah, and you're generating a purely random password, completely random out of that alphabet, the number of possible passwords is still less than 2 to the 80. So we're still not feeling good with those requirements, but it just seems like those requirements are here to stay because users won't sign up for your app. Depending on what it is, they won't sign up if you increase those requirements, if you have them more. You have harder requirements than that. And that's if you generate completely random passwords. So really you need to get up into like 12 characters, purely randomly generated, to be able to be actually secure in that sense. So even your strong passwords, even what's accepted as a strong password, isn't actually going to be secure based on our rule of thumb here. And to make things even worse, most attackers aren't going to use a brute force attack. They're not just going to randomly guess passwords because most of those passwords will never be thought of by a human being. If you're thinking up your own passwords and remembering your own passwords, you're going to use a lot of tricks to be able to remember that won't necessarily be purely random. When have you ever generated a purely random password out of your head? The only people who have randomly generated passwords are if you're using a password manager that manages your passwords and generates purely random passwords for you. In that case, your passwords are secure. I'd say you should use a password manager, but I don't, so I can't say that until I start using one. But I should be using a password manager. Problem is, we're going to like patterns. We're going to use common words or any patterns that we can think of to help us memorize things. And then we're going to do little tricks to be able to get around the requirements for our passwords. So we're going to think of like a word. I want my password to be the string password. Oh, but I need a special character, so I'm going to replace the A with an @ and I'm going to replace the S's with $, and I'm going to replace the O with a 0. There's my password. It meets all the criteria. I'm good. I'm feeling good about that password, right? Meets the criteria, but it's actually a terrible password. It's going to be one of the very first passwords that an attacker guesses, because they're going to throw this into a dictionary attack, which is going to start with, like, you can just Google lists of common passwords. The dictionary attack is going to start with those common passwords. They're going to use variations of them by making these common substitutions, and they're going to be a little smarter about their guesses, not just guessing purely random strings. And they're going to crack a lot of passwords really quick. Like, most people's passwords are going to be broken pretty quick by this attack. Hashing our passwords just isn't super effective. People get in the way. The weakest point in really any security system is going to be the people. If your users aren't coming up with strong passwords, what are you going to do? Give them a message, hey, we were able to crack they register. User registers. Here's my username, here's my password. You respond with a message. We cracked your password in 0.3 seconds. Like, oh, shit. Okay, they come up with another password. We cracked that one in 0.01 seconds. Oh, shit. And then eventually they're just going to not use your site. They're not going to use your site. So it's a trade-off out there. Do you want users or do you want to keep your users safe? It's a very tough question. We could We probably have a whole ethics discussion about that. But anyway, there's another issue. Yeah, I lost my internet, my phone too. I guess nobody can send messages though, except on the hotspot. But there's another attack here. So even with dictionary attacks, we get everybody using password managers. They're generating random strings with enough entropy. Everything's good. There's another attack I want to talk about: rainbow tables, which 1046. I'll try to do it fairly quick. Rainbow tables is going to trade off time and space before they have your hash to be able to crack your hash a lot faster. So with a typical attack, you need the hash to be able to attack it, which of course is always true. You need the hash to attack it. But with rainbow tables, it says, okay, before we find that hash, let's pre-compute a lot of stuff before we have the hash. So what rainbow tables do is they'll have a guess of a password, they'll hash it, they'll take that hash, put it in a function that turns it into something that's a feasible guess for a password. So nobody's going to have, these hashes are super long, nobody's going to have a password that long. So put it in a function that like cuts it down to less than 20 characters or something like that. And then hash that. Throw it in the function, hash that. Throw it in the function, hash that. Throw it in the function, hash that. And just do this billions, trillions, however many times they want. So they're going to generate what we call a chain, which has all these millions, billions, trillions of hashes, however long they want their chains, and then store the first guess and the last hash, or the last guess, I guess, wherever they want to stop. But to store this chain, you're going to take two values, and that's it. That's what you store. With those two values, you have a chain of billions of guesses stored. Billions of guesses of a password stored in that chain. And then you do that billions of times. There are rainbow tables you can find that are gigabytes or larger, which each chain is just two values. And then if you have gigabytes in this rainbow table, it's a lot of chains, with each chain having billions of guesses. That's a lot of guesses, a lot of password guesses encoded in this rainbow table. Huge, huge number of guesses. It takes a lot of time to generate a rainbow table, but it's only got to be done once. Only one time do you have to generate a rainbow table. And there are people who already spent all the CPU power to be able to compute these. You just download them and use these rainbow tables. Now, when you want to crack a hash, you get a hash. Okay, I got a hash. I got a crack. You hash it, you put it in the function, hash it, put it in the function, hash it, put it in the function, hash it. You do that until you reach the end point of any one of your chains. And once you find the end point of a chain, you know which chain contains that password. So you go back to the start of that chain, hash, put it in the function, hash, put it in the function. Do that until you get the hash that you're looking for, and you back up one step. And that's the password. Password cracked, and it's very efficient. You're leveraging billions or trillions of guesses simultaneously, and you can crack passwords extremely fast with these rainbow tables. Very effective, very scary that these things are out there, that your passwords can be cracked, almost instantly, because all the work's already been done. It's already been done and stored in the rainbow table. Very scary stuff. Luckily, we have a very easy solution for this, called salting. So we don't just store hashes of your passwords, we're going to store salted hashes. A salt is a random string, randomly generated for each user, and then appended to the end of your password, and then your password is hashed. And then in the database, we store the salted hash of your password and the salt. And that salt will not be contained in the vast majority, almost zero, of the guesses in that rainbow table. That rainbow table is useless at that point. Completely renders the rainbow tables useless. So we salt. We add that salt to the password, hash it, store the hash and the salt. We do store the salt in plain text. Oh, right. Yeah, good question.
Yeah, where's my laptop?
I mean, my phone isn't connected, so I mean, yeah, I'll just extend the deadline. How do I do this? I'll just leave the lecture question open longer. I'll have a solution, but we got to go. It's 10:51, so I'll have a solution for this. Let's do it this way. I'll just reopen the lecture question next lecture. So on Friday, we'll do both lecture questions. But I'll extend the deadline, so if you remember to do it before then, you can just submit.